Every day, we use plastic without thinking.
Most plastics take hundreds of years to decompose. So we asked a question: can we create a better kind of plastic? This question led to our investigation.
Hello judges, my name is Calista Audrey Rusli,
And my name is Clarissa Ngadimin.
and we are from Sampoerna, Medan. And our project title is called A Comparative Study of Degradation Time and Structural Integrity of Bioplastics made from agar-agar, gelatin, and starch. And today, the materials we'll be using are
Gelatin, agar-agar, starch, measuring cylinder, distilled water, beaker, stirring rod,
silicone mold, and glycerin.
Method number 1, preparation, heating, molding, drying. In this part of our methodology, we first prepared the bioplastic mixtures using agar-agar, gelatin, and starch. The ingredients were carefully measured and mixed. Next, the mixtures were heated to form a uniform solution. After heating, the liquid bioplastics were poured into molds and shaped evenly. Finally, the samples were left to dry until they solidified and formed usable bioplastic sheets. To ensure a fair test, all bioplastic samples were cut into the same size, with a surface area of 3.2 centimeters by 2.8 centimeters. This step is important to maintain consistency, so that any changes in mass are due to degradation and not differences in size. On the first day, we measured the initial mass of each bioplastic sample. The gelatin sample had a mass of 2.79 grams, agar-agar had 2.5 grams, and starch had the highest mass at 3.38 grams. After recording the initial measurements, equal amounts of moisture were applied to each sample to simulate environmental conditions. We then measured the mass at each bioplastic over the next few days to observe changes. On day 1, agar-agar measured 2.5 grams, gelatin was 2.79 grams, and starch was 3.38 grams. On day 2, agar-agar and starch both measured 1.9 grams, while gelatin was 1.8 grams. On day 3, agar-agar decreased to 1.4 grams, gelatin to 1.2 grams, and starch to 1.1 grams. By day 4, agar-agar further decreased to 1.0 grams, gelatin to 0.74 grams, and starch to 0.64 grams. These results show a steady decrease in mass over time, allowing us to track the rate of degradation and compare how each type of bioplastic breaks down.
plastic pollution is a growing global problem.
Bioplastics offer a sustainable alternative by using natural, biodegradable materials.
In this section, we present the findings of our investigation on the degradation of different bioplastics over time. The results show that all samples, agar-agar, gelatin, and starch, decreased in mass over 4 days, indicating that they are biodegradable. Among them, starch-based bioplastic degraded the fastest, while gelatin showed moderate change, and agar-agar degraded more slowly. The graph clearly shows the differences in their rates of degradation. These results suggest that faster degrading materials may have lower structural strength, while slower degrading ones may be more durable, highlighting the need to balance biodegradability and strength in real-world applications. For the conclusion, based on the recorded mass data over 4 days, all bioplastics showed a consistent decrease in mass, confirming that biodegradation occurred in each sample. The results clearly indicate that the type of base material significantly affects the rate of degradation. Starch-based bioplastics exhibited the greatest reduction in mass, decreasing from 3.38 grams to 0.64 grams, indicating the fastest biodegradation rate. gelatin-based bioplastics showed a moderate decrease, while agar-agar-based bioplastics retained the highest mass by day 4, 1.00 grams, demonstrating the slowest degradation. These findings support the conclusion that starch is the most biodegradable among the three materials, while agar-agar provides greater structural stability over time. This difference highlights the importance of selecting appropriate materials depending on the intended use of the bioplastic. In the context of sustainable development and responsible consumption, starch-based bioplastics may be more suitable for single-use applications due to their rapid decomposition, whereas agar-agar-based bioplastics may be preferred when longer durability is required before degradation.
For the real-life application to SDG 12, which is responsible consumption and production. First, identifies biodegradable alternatives to reduce plastic pollution. Second, compares degradation time to improve waste management. Third, evaluates strength and durability for real-world use. Then, supports development of sustainable packaging materials. Next, encourages environmentally responsible consumer choices. Finally, helps reduce landfill waste and environmental impact.
Plastic pollution is a growing global problem.
Bioplastics offer a sustainable alternative by using natural, biodegradable materials.